So thank you, Pierre. Hello, everybody. It's very funny. So I know that more than 100 people are there, but I can't see any face. At some point, maybe I will ask some of you to say a few words. And in any case, if you have any question of whatever kind, please ask. So it's not intended as a proper course like the one you could have during the academic year, but rather a mixture of explanation of some phenomena in number theory and with glimpses of historical remarks. So the general theme is Diophantine equations. So it's the kind of equations which are given by polynomial relations between the unknowns, and the unknowns are assumed to be either integers or rational numbers. This will be my main subject, and of course, if you eventually study arithmetic geometry or stuff like that, there are much more offensive frameworks to study the Diophantine equations, but it's enough for us today. And you'd say that it's enough to furnish an incredible number of still open questions. So roughly, we have three parameters. We have the number of variables, the number of unknowns, the number of equations, and the degrees of the equations. And we could add the coefficients of the equations, but what we want to say will be relatively insensitive to those coefficients. So the title of the talk is 1, 2, 3 and ABC, and the first one could be the number of variables. So let's say 1, and Diophantine equations in one variable. So it's something like this. Let's put my tablet in the right direction. So it's just also needs to have the let's do this. No, it's not what I wanted to do. Okay, so I can't. There's nothing to draw there. Too bad. Yeah, maybe. So we have something like that. A polynomial equations and an an, a0, a1, etc. Those are coefficients. And the unknown is x, and this is a polynomial relation, and the degree is n. And if I want to solve such an equation, like it could be x3 plus x plus 2 is 0 or something like that, then there is a general theorem that there is a bound on the size of the solution. So I will interrupt you just now. I presume that such kind of algebra is okay for you. If it is not, please tell at once so that I can adapt.
You need to give them some time to type answers in the question box.
Okay, so I have, okay. So I could ask a question.
Yes, there's no reaction for the moment.
Okay.
Maybe it's not clear what they should say.
So with such a bound, and I won't prove it, but you presumably you can try to do it. And the idea is I ask that x is smaller than either 1 or this, and so assume that x is greater than 1, and then you say that you use that in here. Okay, and then if I have such a bound, and if I'm only interested in integer solutions, then what's happening? Okay, so I can't move, and then it suffices to try one by one all integers in the interval given by the bound. So even if this bound says me that x is smaller than 1000, then I have something like 2001 integers to check, and that's okay. If I'm looking for rational solutions, then it's a bit more complicated because there are infinite number of rational numbers in the interval, but there is a classic criterion using divisibility that reduces to integer solutions. And then I will assume that the RIs are integers, and then if I am seeking for rational solutions of the form P over Q in lower terms, then Q, the denominator will divide this integer an, and the numerator will divide this integer a0. So in the case where, for example, this polynomial is unitary, there is no an is 1, then it says me that all rational roots are integers. So then I use the previous criterion. And already in that example, one sees a nice feature of number theory. That is, one has to use arguments of two different nature. On this slide, there are arguments relying on divisibility, which are it could be congruences, etc., and related to prime numbers, to coprime integers, and so on. And those arguments are usually not enough, and one also needs to use arguments relying on the size of the numbers. And the first part of the talk is to explain a bit of the geometry of Diophantine equations. So in one variable, this makes no real sense, but I will pass to two variables, and then there will be some geometry hidden. And the geometry, for example, is quite simple. It's degree 1, and it means that from a geometric point of view, if you take equations of degree 1, those are equations of lines, planes, etc. in space. So I'm just describing something which is completely flat in space. And the question is to find the integer points on this flat stuff. And there is a very old problem. So it's so between 3rd and 5th century, the Common Era. And the problem says the following. So now I can't read that, but presumably at least some of you can. And it would be great if one of you could read it loud, but I don't know if Pierre can do that.
Yes, if one of you can translate this, please raise your hand. We'll turn on your microphone.
Well, nobody.
Yes, there is one.
Oh,
well,
great.
The hand disappears all the time. Let me find you by hand. There you go. Ray Tian. You can now speak.
Can you hear me?
Yes.
Okay, so there's a number. When it divided by 3, the remainder is 2. When it divided by 5, the remainder is 3. When this number is divided by 7, the remainder is 2. So what is that number?
Okay, and I have prepared that. With the typo, that's okay. And so that's no problem. Maybe you can read it in Chinese, but I don't know what kind of.
Let me turn on the microphone again. Sorry. You can turn it on, Ray.
And should I just read it in Chinese?
Yeah, please.
有物不知其数，三三数之胜二，五五数之胜三，七七数之胜二，问物几何？
Okay.
I think that's it.
Thank you. So this kind of problem is known today as an example of what is called the Chinese remainder theorem. So it was a Chinese problem. It's due to, so I will pronounce it how I can, so Sunzi or something like that, and published in the Sunzi Shuangqing which means presumably the mathematical classic of Master's Son. That's quite a, you will all agree that it is a nice title for a mathematical book, Master's Son. And here is a reproduction of a page from an edition of the Sing Dynasty. So I'm not sure it's the same page. And it's very easy on the internet to find other pages. And for example, here I have another book, which mathematical book in 9 chapters. It's a later edition, and the big red stamp on it is a stamp of the owner of the book. So I don't know whether maybe it was the cover of the book or the page is not meant to be read. And such exercises have been reproduced in many manuals. So there is a Shuzhou Xiushang, a mathematical treatise in 9 sections, or the Siku Quanshu, the complete library of the 4 treasuries, and which is an encyclopedia. So back to the Chinese problem. So we have a number of things. We count them by 3 remains 2. It means that n, the number of things which we search for, is of the form 3x plus 2. And if we count them by 5, that remains 3. So it's 5y plus 3. And if we count them by 7, it remains 2. So it's 7z plus 2. And the Chinese theorem, or rather the solution of this Chinese problem, teaches us that the smallest solution is 23, and that to get all of the solutions, you just need to add a multiple of 105, which is 3 times 5 times 7. So 3 multiply the 3 numbers that appear here, 3, 5, and 7. In general, what happens is 3, 5, and 7 are pairwise coprime. And so in general, that would be the least common multiple of them, and so on. So I will not teach you how to solve this exercise today. And but just to say that it's the first case is of solving Diophantine equations. The number of unknowns here is something like 4, but the principal one is n, and I have any number of equations. And in general, there are rules given by algebra and stuff called as Hermite normal form or Smith normal form that computers are able to perform efficiently, and that allow you to solve such system. For degree 2, it's yet another language, another country. So it's Greek. So this I can presumably read by myself, but it's ancient Greek, of course. So the pronunciation would be the one I've been taught in school. And I felt that it's funny because pronunciation of ancient Greek by French is not necessarily the same as the pronunciation of ancient Greek by Italian and so on. So it's a problem called the Archimedes' cattle problem. And here that's an edition of 19th century. It does nothing particular except that it's a complete the complete works of Archimedes. Yeah, it's about the cattle of this. It's called the cattle of the sun. It's a Elioyoi ball. And the idea, if we put it in equations, is that there are 4 heads of cattle. So you have cows and bulls of 4 colors. So some are white, and so the cows are lowercase w, and the bulls are uppercase w. Some are black, some are yellow, and some are dappled. And what the problem tells you is proportions of each sort. So, for example, it's told in a very fancy language that the white bulls are 1/2 and 1/3 of the black bulls, to which you should add the totality of the yellow bulls, and so on. And there are a number of equations like that. And you see that's still a degree 1 problem. So you can use the Chinese remainder theorem to solve that. And in fact, if you've done linear algebra, you have 8 unknowns and 7 equations. And what happens is that you can write all, so it will define its maximal rank. It's totally, and it will define a line in the space of the 8 unknowns in the 8-dimensional space. And if you, so you can ask the computer algebra system to solve it, and I did for you. And then I copied I copied the answer. And if you change denominators, you will get that the number of white balls is 10,366,482 times some common integer n, and a number of black balls, etc. And you have those numbers. And that's the first part of the problem. And Archimedes says that, okay, if you do that, you would not be called unskilled or ignorant of numbers, but not yet shall you be remembered among the wise. And so what Archimedes writes is, to be remembered among the wise, you need to solve the second part of the problem. And the second part says that if you add the white balls and the black balls, you get a perfect square of number. So it's something of the form p times p squared. And the number of yellow balls plus the number of dappled balls is a triangular number of the form. So for us, we say that it's of the form m plus 1 divided by 2, because if you take 1 plus 2 plus 3 plus etc. plus m, and it draws a triangle. I don't know if I would be able, no, I won't be able to draw in that software. I'm sorry. I should stick to the one I used to use. Okay. And so that's what we want to solve. And if we write it down, we get something like that. So 17 million and so on times n, it's a sum of the white balls and the black balls. So it's p squared, and 11 million and so on. It's times n, it's the triangular number m plus 1 divided by 2. And so now you can do some algebra. You can factor this 17 million number, and the product with n is a squared. So all prime factors that will appear on the left will have to appear also in n. So n has to be of the form 3 times 11 times 29 times 4,657 times the square, and you get something like that. So n is 4 million, etc., k squared. And the second equation, now it's something like a multiple of n, which is m plus 1 divided by 2. So this is a degree 2 equation in m, and n is seen as a parameter. And so now you know how to solve that. There is this standard formulas for solving degree 2 equations. And you need the discriminant, which will be 1 plus 82 million, etc., times n, to be a perfect square. And I say q squared. And so now I need to solve this equation, which is what this is the 2 of the title. There are 2 unknowns and degree 2, which is a particular equation of degree 2, q squared minus blah blah blah, something I can't read. You see, it's too high and too big number for me. Is 1. And in fact, this problem is known in the nowadays as it's known as the Pell-Fermat equation, and in fact, it was known by Brahmagupta, a Hindi mathematician, something like 1,000 years before. And this problem has been solved in the 19th century and 20th century. And Ilan Vardi has a paper in American Math Monthly explaining how to solve this cattle problem up to the end, and how to write down the total number of animals, which will be a huge number. You see, it has 413, 90, or 91 digits. So that's a very huge number. But Vardi has a very concise formula for that number. And the goal of this part of the talk is to explain how we can solve this equation, and you will agree that we may replace this huge number by a smaller one. So this huge number. So the idea is now we have a parameter which I call n, and I need to find the solutions in integers to the equation x2 minus n y2 is 1. And so if n is 2, then for example x2 minus 2y2 is 1, and I claim that 3, 2 is a solution. So 3 to the square, 3 squared is 9, minus 2 times 2 squared, 2 times 4 is 8. No, 9 minus 8 is 1. And for the second, you could check that 17 squared minus 2 times 12 squared is also 1. And here is the text by Brahmagupta where he explains how to solve that. And this is a text that I can't read, and I spent some hours to be sure that it is the correct passage in Brahmagupta. In fact, fortunately, there is an edition of Brahmagupta's work with an English commentary at the beginning, and I knew from Wikipedia that it was in 1864. It was the correct passage. But looking at the full book, it was very hard to find pages, and I had to learn to write Hindi digits and so on. What you can see on this passage, which is you have 2 lines, and those two dashes just mean that it's the beginning of the line and the end of the line. And sometimes in the full edition, there is also the number of the verse which is written. So here there would be some number written, and here also. And I say verse because this is a book which is entirely a mathematical book, which is entirely written in verse. And so maybe we could play the same words. I don't know if someone can read that. In fact, I don't have the list of all participants, but yeah. So
if someone can read it, please raise your hand.
And if someone can check that I did not make.
It seems nobody is raising their hand, so
okay.
Maybe we're out of luck. Oh well.
That's okay. I mean, if someone wants to read it at some point, or can confirm that I did not say something too stupid, that you would be welcome. So what Brahmagupta says, he doesn't say it using those algebra, but with more complicated phrases. And he said that if x, y, and x prime, y prime are isolations, then you can build a third one, x double prime, y double prime, by these formulas. And so x double prime is you take the product of the 2 x's plus n times the product of the 2 y's, and y double prime is something where you cross x times y prime plus x prime times y. And for n is minus 1, it was an identity that is already present in the works of Diophantine. And the second part of the solution of this equation by Brahmagupta is that from a minimal solution, from one of them, you can build all the other one just by using this identity in a more or less clever way. And nowadays we can give a modern explanation for these identities. You just factor x2 minus ny2 as x plus square root of n times y multiplied by x minus square root of n times y. And we see that this is a product of some, we could say quadratic number because it involves square roots. So x plus square root of n times y multiplied by its conjugate, meaning that I will just change the sign of the square roots. And this is analogous to the relation x2 plus y2 is x plus iy times x minus iy. And in some sense, x2 minus ny2 is a kind of squared norm of the quadratic number. And in the same way that squared norm of a complex number is multiplicative. The squared norm of this quadratic number is multiplicative. So now I take two quadratic numbers, x plus square root of ny minus multiplied by x prime plus square root of ny prime, and then I just use algebra to write it as a quadratic number of the same kind. And here you recognize the x double prime, and here you recognize the y double prime. And so nowadays we can explain this quickly, but we helped by the availability of algebra and the availability of writing just a letter instead of a complicated expression. So we want to solve those equations. And I will go to specific ones to help you understand what could happen. And so I will start by an equation which I call the Pythagoras equation, x2 plus y2 is 1, because it's what happens when I start from the Pythagoras theorem that says that the a2 plus b2 is c2, where when ABC are the length of a rectangle triangle, and I put them, so I assume that the hypotenuse is as length 1. And I want to solve this equation. So in integer solutions, it's clear it's only a plus or minus 1, 0, and 0 plus or minus 1. Those are essentially the 4 vertices of the circle. And so those 4 points. And for rational solutions, maybe the situation is more interesting. In fact, there is a geometric construction that will give us a lot of solutions. So I draw this circle, is a red circle, and I draw the line which is just vertical and tangent to the circle at the point opposite to A. And now I take a point M on this line, and I draw the line AM, and this line will cross the circle in a second point. It crosses at the point A, but it also crosses at a second point. How to see that? You just plug in the equation of the line into the equation of the circle, and so let's say that here it will be y is some multiple of x plus some number, and then I get a quadratic equation in the variable x, and I know one root, which is x is minus 1, and so then I can find the other root. So the intersection point is P, and well, I'll give it just by formula. So if the point M is at height T, then the algebra tells you that the coordinates of P are 1 minus T2 divided by 1 plus T2, and Y is 2T divided by 1 plus T2. So this is a nice formula, because if T is a rational number, that it gives me points, coordinates, which are rational numbers. And conversely, if I take a point P here, which has rational coordinates, and I draw the line AP, it will cross this blue line at the point M, this vertical line at the point M. And you see, if the point A is minus 1, 0, P has rational coordinates, so the usual rules to construct the equation of a line will give me an equation which has only rational numbers as coefficients. And when I intersect two such lines, and I do the algebra for intersecting two lines, I will get a point M which has rational coordinates. So the outcome of this geometrical argument is that with those formulas, I get all points on the circle with rational coordinates. I just need to plug in some rational number T. And in fact, this formula is geometrically classic, because if the height is T, then T will will be the tangent of the small angle BIP, and 2t will be the angle of the 2t will be the angle BOP. And those formulas are exactly the formulas that compute the cosinus, the cosine of an angle in terms of the tangent of half the angle, and the sine of the angle of an angle in terms of the tangent of the half angle.
Antoine, there's a question on your previous slide on the method that you used in your previous slide.
For some reason, I don't see the question. So should I?
No, I'm going to say it out loud. But it's on the previous slide. It's a question from Estefano U. May I ask, why do we multiply x plus the square root of y and x prime plus the square root of y prime in order to solve?
So let me go back to here. So the question is,
I think what was meant is why the top line. Why do you multiply those two?
Okay. So first, it started. All of it started by Brahmagupta, who told us this, that I could have a third solution starting from two solutions. And for example, those formulas, if I apply them to this equation, x2 minus 2y2 is 1, and I apply it to the solution 3,2, and I take twice the solution 3,2 to start with. So xy and x prime y prime would be 3,2, and I compute what I get here. It's 3 times 3, 9, plus n is 2, so plus 2 times 2, so 8. So it's 9 plus 8 is 17. And here I get something like 3 times 2 plus 2 times 3, so it's 12. And I had 17, 12. So this is, it could be magic, and my goal is to unravel a bit of that magic. And so if you are given this statement, you can just try to compute x double prime squared minus n y double prime squared, and do all the computation, and eventually you will manage to prove that it makes -1. It makes 1 as claimed. But that doesn't tell me why this solution, why this Brahmagupta identity works. And so on this slide, I want to explain the Brahmagupta identity. And so the explanation of this identity comes from saying that this is a difference of two squares, and a difference of two squares is usually factored as the first squared plus the first number plus the second number times first number minus the second number. And those numbers, it's x for this, and the second is square root of n times y. And now from this formula, I recognize something as a number of its kind of conjugate. And then I just observe that everything composes, it looks like a multiplicativity of the square norm of complex numbers. And then this is just about one quadratic number, x plus square root of n times y. And if I have two of them, I can just multiply them and write it as a quadratic number with the sum square root of n in it. And I find exactly the quantities that appear in Brahmagupta identity. So in some sense, this procedure explains the identity. And what I could have written on the slide, but I didn't, is that now when you have one solution, and Brahmagupta tells you that there is one minimal solution, and you get all of the one, using this problem. What happens is I take one minimal solution, so say 3 plus square root of 2 times 2, and I put it to some power, k, and I expand this number as something of the form a number plus square root of 2 times another integer, and then it will give me all the solutions of this Brahmagupta equation for this value of the parameter n. I don't know whether.
Yes, there's a comment saying that this answered the question. Thank you.
Oh, thank you. So you see, on this example, geometric example, I was talking about a circle, but what I really used is just that I had a form, the red stuff, which was defined by an equation of degree 2 in 2 variables, x and y, and I was given some point a satisfying the relation. This is just what I need. So in general, the geometric forms defined by polynomial equation of degree 2 in 2 unknowns are known as conics. And in fact, if I have any conic, it could be a parabola, hyperbola, or an ellipsis. Then if I happen to find, I manage to find one solution in rational numbers on the conic, then I will get a parameterizing of the conic of this form. It would be with different numbers, 1 minus t2 divided by or other expression that this formula, but of the same in the same spirit, and that they will give me all the points on the conic. But sometimes on some conics there are no solutions. So in the first case, I take a stupid conic. It's x2 plus y2 is -1, and here there are no solutions because the sum of 2 squares is always positive, so it can't be -1. So it's a conic. I have the equation under the eyes, x2 plus y2 plus 1 is 0. But of course, there are no rational solutions. So I can't draw the form on the real plane. But if I take another conic, x2 plus y2 is 3, then I can. It's a circle of center 0 and radius square root of 3. But then I won't be able to find any points with rational coordinates on it, because there is an issue of congruence modulo 4. The fact is that if I take an integer, assume that let's assume we were looking for integers just to simplify the explanation. If I'm given an integer and I take it squared, so then if the integer is even, the square will be a multiple of 4, and if the integer is odd, then the square will be of the form 1 plus a multiple of 4. So on the left-hand side, x2 would be either 0 or 1 modulo 4, and same for y2. So the sum could be 0, 1, or 2 modulo 4, and could not be 3. So now I have to make a slightly more elaborate argument if I want to have rational numbers instead of integers, but basically it's the same argument. And so on this circle, there is a congruence issue, and I can't find any solution in rational numbers, and so that's it. I mean, the Diophantine equation is solved, but otherwise, it will work in the same way. And there is an important theorem by Hasse it's a 20th century theorem, 1921, that's saying that if there is no sign issue and no congruence issue, then there will be a solution in rational numbers. So here I can make a remark, is that it's not always true that there is a solution in integers. So for solutions in integers, it's still more complicated. There are new issues which I definitely can't talk about here. And this has been explained at the beginning of the 21st century, basically. So it's non-trivial. But in general, for conics, we have a criterion to tell you whether there are no sign issue and no congruence issue. And in general, it works by not only conics, but any number of variables. So I have one degree 2 equations and any number of variables. And there is a way to tell you, to say that there are no sign issues. It's about studying the quadratic form, so those equations of degree 2 in the reals. And there is a more sophisticated way of saying that there are no congruence issues. It's about p-adic numbers. And as soon as the quadratic form has solutions in those p-adic numbers and in real numbers, then it will have a non-trivial solution in Q. What is, well, okay. So I think I will come back to this subject later in the second part of the talk, but I think for the moment, let's be content about that. So the subject of the talk was 1, 2, 3. So now let's go to 3. So I can either increase the number of variables or increase the degree of the equations, and I will increase the degree of the equations. And so equations of degree 3 or more. And here it's another classic text in mathematics. It's Diophantine. So you have the Greek text on the right, the Latin translation on the left, and on the bottom, there is this famous observation by Sir Pierre de Fermat, who was a French lawyer, French in 17th century, and this Fermat is the same as in the former name of the Brahmagupta equation. I written Brahmagupta-Pell-Fermat equation, and in fact, Fermat claimed that he knew how to solve it and posed it as a problem to his mathematical fellows. And Pell, in fact, did not solve it, but Pell was a translator of a German book. I forgot the author of the book. And so I think Euler made a confusion later on and thought that Pell had solved the equation. But in the English word, it's called as the Pell equation. So what Fermat says is that if you, so first, what Diophantine says is basically the solution of the equation x2 plus y2 is z2. So the sum of two squares is a square, and Pythagoras equation. And Fermat says, okay, now if I want a cube to be a sum of two cubes, or a fourth power to be a sum of two fourth powers, etc., 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 then it's impossible to find a solution. And he adds that he has found a wonderful proof of this fact, but unfortunately, the margin is too short to hold it. And this is the starting point for the Fermat's last theorem. And so if Fermat had a proof, we have lost its trace. In fact, many mathematicians tried to solve this theorem later on, and basically all proofs were first wrong, and then people found a way. Sometimes the same guy could find a way to restore part of the proof, and at the same time, inventing new concepts in mathematics. So this problem, which only takes 4 lines to state, has been a source of an incredible number of mathematics. and it has only been solved at the end of the 20th century by Whites and with a bit of help from Richard Taylor. And this is, one should also mention a number of other people like Ken Rivett, whose work is an important step in the proof of Whites, and many other people. So before I look at the equation x cubed plus y cubed is z cubed, and in fact, there is an exercise in tomorrow's problem session about this Fermat equation for degree 3. Maybe it's too tough to be explained in as a problem, but I've written a very long problem list to entertain you, not only for tomorrow, but maybe for the whole summer. So I think if you were wanting to eat math problems, you would certain not to start until the starting of the next academic year. But maybe if people want to discuss or to study this proof as an exercise, we can do it tomorrow. So I will start with a slightly simpler cubic equation because it's simpler to explain what happens. So it's still cubic in x, but in the variable y, it's only squared. So let's start from this equation, and in red, that's the figure it defines in two-dimensional space, and it has two components, and it's called an elliptic curve. And I will play a geometric game similar as the one I played for the circle. I take a point P on the conic, but now on this elliptic curve. So, but now if I draw a line, it will cross. You see, if I draw a line like this, I hope you see my cursor.
We can see it, yes.
Okay, so you imagine that it will cross the elliptic curve in two more points. So what I will fix is the second point, Q, and now I draw the line from joining P and Q. And it crosses the elliptic curve in a third point, which I call P star Q. And this always works like that, because when I plug into this equation the y2 is x cubed minus 2x. I plug y as a linear function of x, and then I get a degree 3 equation in x, and I have two solutions, the abscissa of P and Q, and so there is a third solution, which will be the abscissa of P star Q. There is one special case when the line PQ is vertical. So it means, for example, it should be vertical. Then what happens is that this equation will have supposed to have a root at infinity, and but that's okay. We'll find back this root at infinity later on. So this point P star Q, and what I call P plus Q is just the point which is symmetric to P star Q. And I don't know whether this sentence makes sense to you, but from this rule, these plus rules on the point of the elliptic curve, this defines what is called a commutative group law. It means that it exactly behaves like addition of numbers, except that these are not numbers, these are points. And so P plus Q plus R is P plus Q plus R, and also there is a point which is a kind of zero, such that P plus 0 is P, and in fact this 0 is not a point which is drawn on the picture. It's really this point at infinity, which you get when P star Q, when P and Q are on the same vertical line. And also, if you have a point P, you have an opposite of P, which is just the point which is symmetric. So P plus Q is a symmetric of P star Q, and it's minus. So in fact, the relation is P star Q is minus P plus Q. So the formula could be plus P plus Q plus P star Q is 0. And so I have a commutative group law on the set of solutions. And this group law, incidentally, is a fundamental object in the proof of Fermat's last theorem in general. And more generally, elliptic curves are curves which are defined by a cubic equation of the form y squared minus x squared, and with other parameters here. In the previous slide, it was 2x, but it could be any x plus b. And I need to assume that some expression, which is complicated, it's a discriminant, is non-zero. And there is a geometric condition geometric way to understand this discriminant. It means that when I draw this figure, this red figure, there is no singular point, nowhere, no place where the curve either has a cusp or crosses itself. And so those are curves, look like curves in any case. But contrary to what happened to conics, there is no way to parameterize those curves by rational functions. And this is how those elliptic curves appeared in history. People wanted to compute integrals with a denominator some square root of a polynomial of degree 3. Like imagine you want to compute integral. Yeah, I'll try to do this. I will try. Presumably you can't see anything now, but I will.
For the moment, we still see your slides.
Yeah, I know. So I need to understand how to share something else. That's not about the webcam, it's about here it is, affiché, right. So imagine people wanted to, can you see that? People want.
Yes, now we see a pad, yes.
Yeah, you see a pad and I lost my work. People wanted to compute such integral. Do you know about integrals? If you don't, it will. This explanation will make no sense. But
the people are saying yes in the comments.
Okay, good. Why did they want to compute integrals? Because they wanted to compute the length of mathematical figures. And when you want to compute the length of a curve or the surface of a surface, the area of a surface, you need to compute a one-dimensional integral or two-dimensional integral. And if they wanted to compute the length of some curves, they were able to compute it using classic functions. Like you know how to compute the length of the circle from its equation. But they wanted then to compute, for example, the length of what we'll call a lemniscate. So more complicated curves, and they always found such integrals, and there are no way to solve it. But then the idea of people was, if you had this, you just write that, and it was something like dx over y, so such integral. And sorry, yeah, dx over y. And this is the way, this is how elliptic curves entered the field of mathematics, because they were used to compute the length of an ellipsis. And we'll see, and maybe no, we won't see it, but contrary to conics, elliptic curves cannot be parameterized by curves. So now there is a solution of a classic Poincaré conjecture by Mordell in 1922, is that for elliptic curves, those solutions form what is called a finitely generated abelian group, which means, and this is how Poincaré phrased it, that you just need to find a finite number of solutions, you don't know how much, on your elliptic curves, and then you can get all other solutions just by playing this geometric game of taking 2 points and getting a third one. To prove the theorem, Mordell had to invent a lot of interesting mathematics, and this is really a masterpiece of Diophantine geometry. And what Siegel proved soon after is that, for example, if A and B are integers, then you have only finitely many integer solutions. So quite a different behavior than for degree 2, where we had a lot of integer solutions generally. And in degree higher than 3, then it's more complicated to state the theorem because I need to, for elliptic curves, I had this non-zero discriminant condition, which means that there is no singularity in some sense. In higher degree, one needs to be sure that there is no singularity which is hidden anywhere, so even in complex numbers or at infinity. But let's just don't pay too much attention to those details. And Faltings proved in 1983, this conjecture of Mordell, that there are only finitely many rational solutions.
Antoine, if you're done using the block note,
I'm sorry.
You should share the slides as well.
Exactly.
I just realized you weren't commenting on what you wrote anymore. Sorry.
So I just put back the theorem of Mordell and the theorem of Siegel that are only rational solutions. So you could generate all rational solutions from a finite number of them, but for integer solutions you have only finitely many. And for in degree higher than 3, so 4 and higher, up to some condition which is complicated to state here, there are only finitely many rational solutions. And in particular, the Fermat equation is x4 plus y4 is z4, but I can put it in lower terms, so write it as x. So I'm going back to my pad and oops, no. So but it's I could write it like that. And so it's a degree. It's a degree 4 equations in two unknowns, A and B. And there is, in that case, there is no singularities and so on. And a consequence of Faltings' theorem is that for every integer n greater than 4, the Fermat equation has only finitely many solutions. And this was already also this has no consequence for the final proof of Fermat's last theorem, but it was already an important step. And just to conclude, just say that we have seen 3 classes of equations: degree 1 or 2 conics, degree 3 elliptic curves, and degree 4 or higher. And the behavior is different in each case. For degree 1 or 2, we could parameterize the solutions, and sometimes there were infinitely many integer solutions. In degree 3, we have no rational parameterization, and sometimes infinitely many rational solutions, but always finitely many integer solutions. And in degree 4 or higher, finitely many rational solutions. And this is the complicated trichotomy one. And in fact, that's not the good way to understand it. And the correct way of understanding this is really to put geometry and to consider complex solutions. So now they will form a surface, those complex solutions, because I have two complex numbers. So it's something like a space of dimension 4. And I add one complex equations, and a complex equation, there are two relations, one for real part and one for imaginary part. So I will obtain something which is like a surface. And Riemann in the 19th century invented the notion of genus of a Riemann surface. And in genus 0, it's something like the sphere, and the curvature is positive. And in genus 1, it's something like a torus, it's a donut, in genus 1. And in genus 2 or higher, it's a donut, but with many more holes, not only one hole, but many holes. And then it's something like negative curvature. And this is the correct way to understand what happens, except that nobody, well, not nobody, but in some sense, there is no proof of what happens in those cases just by this point of view of positive or zero or negative curvature. I mean, all proofs are different, but at some point, they will exploit those geometric properties. And in higher dimension, that's remarkable that despite all the progress of the 19th and 20th century, the situation is wide open. So there is an analog for the condition genus greater than 2, which is called a variety of general type. And there is a conjecture by an American mathematician, Serge Lang, that predicts that the rational solutions must be contained in a subvariety. So to say it in simple words, if you look at the rational solutions, they will always satisfy additional algebraic conditions, which you cannot guess on the initial system of equations. And it's known in very few cases, which are complicated to explain. It's called subvarieties of abelian varieties, but that's okay. One case I can try to describe is a conjecture of Euler. So Fermat's last theorem says that if a sum of two cubes cannot be a cube, Euler conjectured that a sum of three fourth powers could not be a fourth power, and similarly for higher degrees. So a sum of of 4 a fifth power could not be a fifth power, etc. And in fact, this conjecture of Euler is false. There was a counterexample in degree 5 found around 1965 by computer search. So it was the beginning of the of very powerful computers, and the mathematicians tried to find counterexamples, and they found in degree 5, but they did not find counterexamples in degree 4. And this counterexample came by the American mathematician Elkis in 1987 with this incredible relation, which I won't read because it's number of 2 million something plus etc. So a sum of 3/4 power, which is a fourth power. And Elkis did not find this example by brute force. This would not have worked. He did geometry. So he understood that this surface with equation x4 plus y4 plus z4 is 1, could be viewed as a family of elliptic curves. And now, using all the theory of elliptic curves, he could find an appropriate elliptic curves in this family, which have points, using all what is known about elliptic curves, and especially theorem which were quite recent, 1978 or something like that. So it's a very nice paper, beautiful theorem. And afterwards, another mathematician, Frey, asked Elkis whether his solution was the smallest one. And in fact, it is not. And so using an extensive computer search, but they did it not in a very clever way. So they observed that some congresses must hold, etc. So to divide the space of where they are looking for counterexamples, and they found he found the smallest counterexample, which is still very big. And okay. So now I think I'll have part time for part 2, and we'll skip part 3. You'll say the important question is to decide whether or not the Diophantine equation can be solved, because despite all the complexity of the previous discussion that in genus 0, 1, or 2, the picture is quite different geometrically and number theoretically. It's still an important question to just say whether or not a system, Diophantine system, has solutions. And it was such an important question that the German mathematician David Hilbert posed it at the 1900 International Congress of Mathematicians. So we have in many languages, and yet one more, it's German. So he asked about the Entscheidung der Lösbarkeit einer Diophantischen Gleichung, which means that he is given a Diophantine equation in any number of unknown and coefficients being rational integers, and he asks to find a method by which, using finitely many operations, one will distinguish whether the equation is solvable in rational integers. So at that time, it was 1900, the notion of an algorithm was not clearly stated out, but Hilbert asks for a method, and using finitely many operations. So today we recognize the idea of an algorithm. In fact, in 1928, Hilbert generalized his problem one step further, and now it was called the Entscheidungsproblem, the decision problem. So here it was Entscheidung, the decision of Diophantine equations, but now it's a decision of anything. He asks for a method that correctly answers by yes or no to every mathematical question that you could ask it. So you want to ask whether the Riemann zeta function has zeros, or all of its zeros of real part 1/2, and then assume that you can tell it in a suitable way to the computer or the algorithm would tell you yes or no after finitely many steps. This was very very bold, but in fact, a lot of the mathematics of the 19th century or beginning of the 20th century were hinting in that direction. That because in many cases there are procedures to define to tell whether things are true or not. There are procedures in geometry, for example, all the classical geometry that you learn at school can be formalized in this way, and algebraic geometry, which is more sophisticated, but it's also there are algorithms. They are not very efficient, and subsequently in the 20th century, people invented efficient algorithms, but the question was already to have an algorithm. And in 1936, Gödel, Turing, and Church proved almost simultaneously, within a few years, that no such algorithm exists. So I keep the 3 names because all 3 papers by Gödel, Turing, and Church, they're all written in different fields. Gödel was doing first-order logic. Turing invented Turing machines. I mean, it's an abstract model of a computer, and he asked so whether if you give a program to a computer, the important question is to know whether the computer will halt at some point or not. For example, it would be nice if whenever you make a computer program, the compiler could tell you, wait, I'm certain that your program will run forever. And in Church, it was something called lambda calculus, which was another formalism for mathematical logic. So three different areas of mathematics, but all converging to the same negative answer to the decision problem. Nevertheless, the decision problem which is solved negatively is a general negative problem. It's not the one that Hilbert has asked for in 1900, and one may still hope that this problem has a positive solution. Well, I mean, maybe we could hope before 1970, because the Russian mathematician Matiasevich proved in 1970 that there is no such algorithm. So what he does is something incredible, because what Matiasevich proved, and these other names should have been included in the name of theorems, namely Julia Robinson and Putnam. And they prove that the complexity of Diophantine equation is as large as the complexity of any mathematical problems. They prove that, Matiasevich proved that any mathematical problem can be rephrased as a Diophantine equation, but the degree would be enormous, and the number of solutions, or the number of variables would be enormous, etc. But the Diophantine equations have the same complexity as mathematics. And for example, there is a very strong version. There is a polynomial in 10 variables, and of those variables, 9, the first one t is a parameter, and the 9 other one are the one in which you want to solve. So there is no algorithm that can tell you, given some value of the parameter t, whether the equation f of this parameter x1, x9 is 0 has a solution in 9 integers or not. So I say that it's a huge number of variables and so on. It's not so huge, it's 9. And for rational solutions, it's still unknown. So you see, if you replace integers by rational numbers, then we don't know whether the decision problem has a positive or a negative solution. People believe that it has a negative solution. There is recent work by people like Königsmann, Björn Kuhn, Alexandra Schlattenkor, and so on, that hint to the fact that the answer is negative, but we don't know. And in degree 2, well, maybe it's still possible, because you see, you have, in this case, we need 9 unknowns to have a negative solution. So maybe in degree 2 there is. In fact, in genus 0, the Hasse-Minkowski is very explicit. So it will allow you to decide effectively whether the solution of degree 1 or 2 are the rational solutions. In genus 1, there is an upper bound for the size of an integer solution. This is the theorem of Alan Baker, slightly before 1970, and that earned him a Fields Medal. So there is a bound in the same spirit as the initial bound for one equation of any degree. And so if you have a bound for the size of an integer solution, you can just try all solutions, or all integers below that size, and you say. For rational solutions, it's still unknown, in fact. So in 1974, the American mathematician John Tate invented a way to that in practice always furnish you the finitely many number of points by which you can generate all of them. But it's still a conjecture, because this what is known is that this device works if some complicated object called the THFRH group is finite, and if this group were not finite, then there would be no method. And in genus greater than 2, it's completely open. Nobody, if you take an equation of degree 4, for example, nobody has a way to compute an upper bound, general upper bound for the number of possible solutions. And the ABC conjecture is a conjecture, but it's a way to get this solution. And what is nice with the ABC conjecture, and it has been stated by Oesterlé and Masser. So Oesterlé is a French mathematician, and Masser is a Swiss mathematician. No, he's Australian, I think, but he works in Switzerland in 95. And it's a very elementary expression. It says that if you have 3 coprime integers, such that a plus b is c, then the maximum of the size of ABC is smaller than some constant times what is called the radical of ABC to some power. In fact, to any power greater than 1. And the radical of ABC is a product of the prime numbers that divide it. So what this says is that if I have an expression of the form a plus b is c, then in a, b, c, I have all the exponents of the decomposition into prime factors appearing as exponents. And here in the radical, there are no exponents by definition. It's just the product of all the primes with multiplicity 1. And the exponent can be theta, so it can be anything greater than 1 up to this constant. And it means that in average, the multiplicities of the prime factors cannot be too large. And the record, if you assume, for example, that k theta is 1, so in some sense the highest ABC triple, which is known, that has been found by retrace in 87, is just 2 plus 3 to the 10, 109, is 23 to the 5th. And then if you look at the quotient, it's 1.63, it's quite small. And what is very nice from this conjecture is that if you solve it, then you're really a master in numbers, as Archimedes would have said. Because, for example, you can solve the Fermat's theorem in 1 slide. So assume that I have a non-trivial solution of the Fermat equation, xn plus yn is the As usually, you can divide by the x and y and z by a common denominator, a common greatest common divisor. And then all these integers are coprime. And I will apply the ABC conjecture with a is xn, b is yn, and c is zn. And now the radical of some power is just of xn, y, and zn. So the prime numbers which appear in this product here, here, is just the same prime numbers which appear in x, y, z. So the radical here of x, n, y, and zn is the same as the radical of x, y, z. And so now, assuming the truth of ABC conjecture, I will get the supremum of x, y, z to the n is smaller than k theta times the radical of x, y, z to the theta. On the other hand, the radical of x, y, z is smaller than the product of x times y times z, because here I have all prime numbers appearing in x, y, z with some exponents, and here I have the same prime numbers with exponent 1s. And the product of 3 numbers is smaller than the largest of them to the cube. So finally, I get that the supremum of x, y, z to the n is smaller than some constant times the supremum of x, y, z to the 3 theta. And now if n is greater than 3 theta, I get that x, y, z are smaller than this expression, k theta to the 1 divided by n minus 3 theta. And here you see that if n is large enough, this constant k theta to some exponent, which goes smaller and smaller, eventually it will be smaller than 2, and strictly smaller than 2, and so that shows that x, y, z are very small. And I can check that will not give me solutions. Okay. So that's one reason why it's important to solve the ABC conjecture. One nice remark about the ABC conjecture that it can be solved for polynomials, but maybe I will skip. Let me check. I think I can try to say. So for polynomials, if you take an equation of the form a plus b is c, where a, b, c are polynomials without common factors, and coefficients can be complex numbers, then there are objects in number theory which are analogs of the radical and the supremum. So one replaces the size of the numbers ABC by the supremum of the degrees, by the degrees, and one replaces the radical of the ABC by the number of complex roots without multiplicities. The reason for which we do that, or we know that it's interesting to do that, is that both rings, the ring of integers and the ring of polynomials in one variable, have very close algebraic properties. They both have a Euclidean division, and prime numbers correspond to polynomials of degree 1, and so on. And on the other hand, the ABC conjecture for integers is an ABC theorem for polynomials. And well, maybe I can skip or I will skip the proof. And so the proof is one slide, but I skip it. So
can I ask a question on this argument from Vlado Petrusenko? But does this only hold for big enough n or for all n?
No, for you need n big enough, but in ABC it's supposed to hold for any theta greater than 1. So if you take theta very close to 1, this will be as soon as n, or maybe assume that you use it for n is something in between 1 and 4/3. Then this will be this will at least gives you a finite number of solutions for each Fermat equation, and only non-trivial solutions for n large enough. And of course, and if you don't know what the constant is, k theta, you can't do anything, because then it could be a very large bound, which depends on n, and it's impossible to, unless it is effectively given, you don't know how to make the search. But in principle, you have the solution.
Thank you.
For polynomials, it's better because there are no constant, no implicit constant here. It's just a plain inequality. And in the same way that we proved that ABC implied Fermat for integers, we can prove, for example, that the Fermat curve cannot be parameterized by rational functions. I remember I said that elliptic curves could not be parameterized by rational functions. And for example, if I take I can prove it for the Fermat equation. So if I have coprime polynomial PQR such that Pn plus Qn is Rn, and apply the ABC identity, I get n times supremum of degrees is smaller than number of common roots, or number of roots of PQR -1, and the number of roots of PQR is smaller than sum of the degrees -1, and this is strictly smaller than 3 times the supremum of the degrees, and so I get that exponent n is smaller than 3. And here I have no how to say. Well, no exception, and no finite number to test. I think I will skip 5 or 6 slides. So this ABC conjecture implies Fermat. It also implies an effective version of the model conjecture. And then maybe it's a good time to end the talk by by an event that appeared almost 10 years ago. So in the New York Times, it was big title, possible breakthrough in explaining a mathematical riddle. And it was about a Japanese mathematician, Shinichi Mochizuki, who had possibly who had announced a proof of the BC conjecture using a theory that he had developed in the previous years, theory which takes an incredible amount of pages to develop. But the story did not happen very well. So, for example, many important mathematicians could not really understand what happened in the paper. And in 2013, so there was a blog post, which I found very interesting, called The Paradox of the Proof, where two mathematicians explained to journalists their opinion about this proof. And this opinion is not really an opinion about the proof, it's an opinion about what they can't understand from the proof, which is important. So the first one said he decided he can't possibly work on this, that would drive him nuts. So this is what happens where mathematics is too complicated. Let's say you try to read it and you can't, and you have the impression you get crazy, and so sometimes you stop. So it's hard to stop when you do math, because you have to study math, because then you want to get the exam and so on, so you have to work on it. But sometimes you feel defeated, and if it's not your math, you're allowed to be defeated. If it's something you want to work on, then it's more complicated. Sometimes one has to admit that one is defeated. And so the second answer is, in fact, more important to me. It's important to be read by every people who will do math eventually. So it's that you don't get to say you've proved something if you haven't explained it. A proof is a social construct. So that means that really you can say you've proved something, but if the people who want to read it don't understand it, you need to say it again, possibly in other ways, and you need you will need to find better words to explain the proof. And the proof is also a social construct that is not clear when you read math in the 20th century, but if you read math from the previous centuries, then it is clear that what people could prove earlier is possibly not what we could prove today, and maybe the details are missing, or maybe and maybe sometimes an argument is incorrect. There is an equation from mathematical physics that Klein, the great mathematician Klein, solved in the 19th century by saying it's called the Laplace equation. It's just he wanted to solve the equation. He said, okay, I built myself a form, a physical form in glass, and I will put some metal part at the point that interests me, and some electric charge at some other point, and I will look at the electric field on the material, and this will solve the Laplace equation with such and such conditions. And this is a very strong argument to understand what the equation means and what the solution means, but this is not a mathematical proof because it relies on objects of another world. But for Klein, it was enough. For mathematicians of later years, it was not, and people managed to prove solutions. And the second point is that if the community doesn't understand the proof, then you've not done your job yet. So I mean that one has to go out, and one is not working just for oneself, but for the community. That was 2013, and then a lot of people worked, many people worked, and finally, 5 years later, the two mathematicians, German mathematician, Peter Scholze and Jakob Stix, and Peter Scholze got a Fields Medal 3 years ago. And they read the paper in detail, and they found that at some crucial point, an argument is not enough. And so they explain why ABC is still a conjecture. And I think it's a perfect time to stop. So thank you very much.
Thank you very much, Antoine. Please join me in thanking Antoine Chambert-Loir for this very enlightening lecture. I will now call for questions. So once again, you need to type them into the question box. This may take some time, but there's already a few questions in there that I can ask.
Okay.
Oh, please go ahead. You wanted to say something?
No. Maybe I wanted to say a few words about the organization of tomorrow's exercise sessions, but I can do it after the question.
Okay. Then let's. I'll try to remember.
Otherwise, it's not. we can discuss that tomorrow. But I will say a few words.
So here's a question. Oh, sorry. Here's a question from Leonardo Carmo on the Hasse-Minkowski theorem that you presented earlier. So if we can homogenize the Diophantine equation, can the Hasse-Minkowski theorem be applied to integers?
Yeah, but if the equation is homogeneous, that it makes no difference, no real difference to solve it in integers or in rational numbers. So, for example, I will take a hop. I will take. So I need to know how to get a new page. No. No. It's incredible. New page. So, for example, if you have something, if you want to solve x2 minus 2y2 is 7, and if you want it homogeneous, then you would have x2 minus 2y2 is 7z squared. So Hasse-Minkowski tells you about this, but not about this. Oh, sorry. Yes, no, you can read. So that's a step, but that's not enough. And this is exactly. So if the initial equation was already homogeneous, then Hasse-Minkowski is enough. But if it is not, so if you have quadratic terms and linear terms and constants, like in this example, then you need more arguments to understand whether this equation has solutions in integers or not. And those arguments have horribly fancy names, such as étale cohomology, Brauer groups, and so on.
Thank you. There was another question from an even earlier part of your talk. I think it was almost the very first slide, apart from the title. A question from Agaz Mahayan, or Mahayan, I'm sorry, where you presented a bound on solutions given by the supremum of the coefficients on of an equation.
Yep, go back, but first I need to this. So I think I wanted to go to the first page, but what I put it is size is 1%. Okay.
Yes, exactly that one. Yeah. And so the question is, can this supremum bound be improved?
Yeah, yes and no. I mean, for example, yes, I can say it can, but there are various bounds to do that, and usually they're not so good. Why this bound is not so good is because you see the A1 is just appeared as multiple times x, but AN appears as multiplied by xn. So one would like to weight the coefficients here according to their position. But except for that, so it's not the best bound. But it's hard to get a very good bound. But the mathematics of the 19th century, and I don't know at what stage of study you are, but I know roughly what age you are. But I've heard that you already learned a lot of mathematics by yourself or in mathematical competitions and so on. So there is a field called holomorphic functions and complex function theory. And then it was very important to devise methods to compute the size of the solutions or to understand where the solutions of such equations are. So in the 19th century, there are a lot of inequalities like this that were invented. And sometimes for a given equation, one of those inequalities can be better than the other.
Thank you. There's a question of Takue Asai, who first thanks you for your beautiful lecture. And he then says, in the lecture you said that the ring of integers and the ring of one variable polynomials are very similar to each other, but it seems that the integer ring is more difficult to tackle with. For example, there are some problems which are already solved for polynomial rings, but remain open for the integers.
Very good remark.
So what do you think is the factor which makes them, the integer ring, more difficult?
So that's a very, very, very good remark. And there is one tool. Do we have 2 minutes? If
yes,
I have
yes,
2 minutes,
have 8 minutes.
If I have 2 minutes, okay, so I have 2 minutes, I will give you the proof of ABC for polynomials, and then you'll see. So you see, I want to prove that if I have 3 polynomials such as a plus b is c and coprime, then the sum of the degrees, the supremum of the degrees is smaller than the number of roots, -1. And so the trick is to introduce this quantity, which is a times derivative of b minus derivative of a times b, which, as you can check, is also ac prime minus a prime c or cb prime minus c prime b, just by algebra. And so now the polynomial d is non-zero. This is maybe it should have been stated on a hypothesis that the ABC were not constant, but the coprime is really not enough. So it's non-zero, and the degree of d is smaller than here. When I take a derivative, the degree lowers by 1. So if I multiply by a, I will get degree of a plus degree of b minus 1, and same for this term. So the degree of d is smaller than degree of a plus degree of b minus 1. Now, if I have a root of one of those polynomials, ABC, with some multiplicity m, it will be, so imagine that it is a root of multiplicity m of a. It will be a root of multiplicity m of this factor, and this root will have multiplicity m minus 1 in the derivative, and possibly not a root of b. So it will be a root of multiplicity m minus 1 of d. And that's the same, thanks to those equalities, it's the same for each root. And so it means that the degree of d is at least the sum of the degrees that will give me all roots with their multiplicities, but it will be m. Each root will appear with its multiplicity in a, b, or c, but there is this -1, which I have to take care of, and so I have to subtract this number of total roots. So I have this inequality, and so now I have degree of d, which is smaller than something here, and which is greater than some other thing here. So I do the algebra, and I get that the degree of c is smaller than the nu of ABC, number of roots, -1. And by symmetry, I have the same result for A and B. And that proves the ABC conjecture. So what was the trick that made this proof possible? Is just that I could differentiate polynomials. And you can think of whether you can differentiate integers, but nobody can. I mean, there are ways to differentiate integers, but for example, if you want to do it if you want to do it so that the standard root of calculus applies, when you have a polynomial A and you divide it squared, no, sorry. If you want to divide, to take the differential of 1, it has to be 0, because you have 1 squared prime, which should be 2 times 1 times 1 prime. And so this is 1, so you have 1 prime is 2, 1 prime, and so 1 prime is 0. So if 1 prime is 0, then 2 prime, which is 1 plus 1 prime, has to be 1 prime plus 1 prime, because the sum of the derivative of the sum is the sum of the derivatives, so it has to be 0 as well. And so you see that all derivatives of all integers are 0. So there are no easy way of defining the derivative of an integer, and because of that, all the proofs that happen that work very well for polynomials and which use derivatives cannot be translated for integers. And people worked very hard at the end of the 20th century to try to invent a derivative of integers, but up to now it did not work.
Thank you. This really illustrates the difference between the two rings. Here's another question from Stefan Pajaniraja. Do Diophantine equations have an application in cryptography? Yeah. So yes and no. No, because yes, because world of cryptography uses elliptic curves a lot. I mean, in your credit card, or in whenever you open up a HTTPS website, you have an elliptic curve running under in the computer. But no, because these are not Diophantine equations in integers, but rather in finite fields or incongruences. So it's elliptic curves mod P, but not elliptic curves in the same sense as the one I described today, but you can elaborate. And so the invention of elliptic curves mod P, or it was the work of mathematicians at the beginning of the 20th century, Emil Artin, Japan, so in Germany, Helmut Hasse in Germany, André Weil in France, Takagi in Japan. And basically, the complete understanding came for elliptic curves and stuff like that came around the 1940s in France with André Weil. And for Diophantine equations in the higher number of variables, this had to wait for the work of Grothendieck in inventing étale cohomology, and Deligne, who proved what is called the Weil conjectures in 1973 or 4. But now elliptic curves are used in cryptography because they have this group law that I described geometrically, and it works also for finite fields. And this group law is very useful because you can cook up a version of the RSA algorithm, reverse Shamir-Edelman algorithm, using elliptic curves, or you can you can use this group to make cryptographic system. Thank you. We've got enough time for one more question. A question from Min Nguyen. Quite an open question. Is there a connection between elliptic curves and combinatorics? I'm tempted to say yes. There are, so for example, the work of the German mathematician Jacobi in the 19th century are full of formulas that link elliptic curves to some objects that are called modular forms, and modular forms are absolutely related to combinatorics. But also, for example, next page. If there is a theorem of Fermat that if P is a prime number,
which is congruent to 114, then you can write P as a sum of E squared plus B squared. But the A and B, the A and B correspond to some elliptic curve. Not P. So yes, in some sense, yes.
Thank you very much. Thank
okay.
you very much, everyone. For oh, sorry, I didn't mean to interrupt.
No, that's okay. Well, I have to add one thing about tomorrow. What we are going to do tomorrow. So
yes, please do.
I don't know how did the other exercises session happen. If you've downloaded the list of exercises that I proposed, it's very huge, and it's not my goal that we tell something about each of them. It's really my goal that all of these exercises will entertain you. So maybe tomorrow the good idea would be to split into rooms where people want to study one part of the list or another part of the list, and so if you have time tonight or tomorrow or whatever to browse the list and to decide for which exercises you would have much more fun, and decide, and then tomorrow when we meet, it would be at 7 o'clock Paris time, we can split up in rooms that do that. If you manage to do that, I don't know. I hope so.
There's a forum where this can be organized. Maybe this is a good place to do that. So we've already seated the students in the different rooms, but
okay.
In view of this, maybe this can be changed. So this can.
You're talking about the Discord forum, or there is another one?
No. There's an actual forum now on
in
the,
Gazaton.
No, on the website of the.
Oh,
of the
okay.
school.
I don't know. So well,
it just appeared 2 days ago or 3 days ago.
And in any case, the forum won't be destroyed after the conference. It will stay for some days or months.
It should stay for some days or months. I don't have the exact.
It could stay all over the summer if people wanted to go on chatting about.
Oh, to continue talking about the exercises. That's an excellent idea, indeed.
Oh. Well, all of you need to have some rest at some time, as much rest as you need.
It's very resting to do some exercises in number theory. Yes. Okay, so please join me in thanking again very much Antoine Chambert-Loir for his very, very interesting lecture, please.